So in today's lesson, we're going to learn about the relationship between Kw, Ka, and Kb. Those are our equilibrium constants associated with acid-base equilibria. But before we begin, I want to give you some context as to when we might need to perform calculations like we're about to perform. So you'll notice that this is an excerpt from the table in the back of our textbook outlining the Kb values for some weak bases. And, this is a very short list. Many more Kb values exist. But these are some that are presumably used to solve some of the problems in our textbook. But let's say, for example, that I were looking for the Kb value for a question that required me to know the Kb value for the nitrate ion, NO3-. Well, how would I go about it? It's not on the list. Well, it turns out, and I'm going to write this out, that we can determine or calculate, the Kb value of a base if we know the Ka value for its conjugate gut acid. So in other words, if I were to look up the Ka value for HNO3, that is the conjugate acid of NO3-, that would help me to determine the Kb value for NO3-, right? So just a quick reminder, how is it that we go about finding what the conjugate acid is? Well, we go ahead and we react that substance with water. And if in this case NO3 is acting as a base, it's going to be accepting a proton from water. And then we just go ahead and show the product there. So the product would be HNO3 and OH-. And that's why this is acting as a base, of course, because we can see that it's producing hydroxide ions. Okay, so again, if we want to know the Kb for this guy, we need to know the Ka for this guy. And that's what today's lesson is going to be all about. How do we get around the fact that, the table, the Kb table in a particular resource may not give us all of the Kb values that we need? What is an alternate method of calculating this? So we say that in general, for conjugate acid-base pairs, that Kw can be used in order to find out Kb, because we know that Kw will equal Ka times Kb, where, and let's be really careful about this, where we have acid-base conjugate pairs. Okay, so for instance, if I wanted to find out the Kb value for SO3, so the Kb for SO3, SO4 2- I should say, I don't know that. I would need to use the Ka for its conjugate acid, HSO4-, and that's a value I know. It's right here in the table. Okay, so without further ado, let's take a look at a practice question. So in this question, it's asking you to determine the Kb for the fluoride ion. So again, we're going to remember that to calculate the Kb for a particular substance, we're going to use Kw along with the Ka value for the conjugate acid. So here are a couple of reminders. First of all, Kw is equal to 1.0 times 10 to the negative 14. And we're going to assume that this reaction is taking place at 25 degrees Celsius. Now, the second thing I want to do is I'm going to go ahead, I'm going to write out the process of F- accepting a proton, it acting as a base, so that we're clear on the conjugate acid involved. And so I'm going to do that next. So if I have F-, and I'm asked to find its Kb value, then it's acting as a base. And so I'm going to react it with water. And in so doing, F minus is going to act as a base and accept a proton from water and become HF. And that's also going to create our hydroxide ion, which is responsible for that alkaline pH we're going to get. And so, you know, what do I have here? Here is my base that I'm looking for the Kb value for. And over here I have HF, and this is my acid, the conjugate acid. And so it's the value, the Ka value that I'm looking for in order to solve this problem. So I'm going to go to my resource section in the back of my textbook, and I'm going to look to find hydrofluoric acid, HF. And I can see it. Let me see. Where is it? Hydrofluoric acid. Its conjugate base is F minus, and the Ka value for HF is 6.6 times 10 to the negative 4. So I'm going to go ahead and go back and write that out. Let me just double check that. 6.6 times 10 to the negative 4. Okay. So my Ka value is for my conjugate acid is 6.6 times 10 to the negative 4. And so now I have all the information that I need in order to solve this problem. So I'm going to go ahead and do that. So I know that Kw is equal to Ka times Kb, or Ka and Kb are conjugates. So isolating Kb is going to be equal to Kw divided by Ka. So 1.0 times 10 to the negative 14 divided by 6.6 times 10 to the negative 4. And I'm getting a 1.5 times 10 to the negative. Let me count those zeros out. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And so, you know, so that's, what have I found here? I found that the Kb value for F minus is 1.5 times 10 to the negative 11. Now, let's see if that makes sense, because we talked earlier about the relationship between acids and bases when they're in acid-base conjugate pairs. And typically, if we see that an acid is stronger, we see a base that is weaker. And that seems to be the case here. So that gives us an impression of the relative strength of HF versus F minus as an acid and a base, respectively. Okay, let's look at another example, and I'd like for you to see if you can do this on your own. So the question reads, determine the value of Kb for dihydrogen phosphate, H2PO4. And I'm going to give you a bit of a hint. H2PO4 is an amphiprotic substance, and so it can gain and lose protons. So you're going to have to do some searching. Give that a try, and when you're ready, resume the video. And so I'm hoping one of the first things that you did was to go ahead and write out the ionization of this substance acting as a base, okay, our dihydrogen phosphate. So I'm going to go ahead and do that. Because we need to know what Ka value to seek out. And so if I say H2PO4 minus reacting with water, and again, if I'm looking for the Kb value for this particular substance, then it's acting as a base, right? And if it's acting as a base, then it's going to be accepting a proton from water, and it's going to become H3PO4. And that's going to liberate some hydroxide ions. And so the Ka value that I'm looking for is the Ka value for its conjugate acid. And that's this guy. And so you hopefully started there and realized, oh, wait a second, what I have here is a polyprotic acid, so I need to go to my polyprotic acid chart and look up the Ka value for phosphoric acid. And so when you go ahead and you do that, you see that for phosphoric acid, here it is, its conjugate base is that dihydrogen phosphate ion. And so this Ka value is going to be the Ka1 associated with it, because we're looking at phosphoric acid right here, having and it having lost its first proton, right? So the conjugate base of H3PO4 would be this guy H2PO4 minus. And so if we're looking for the Kb for it, we need to look at the Ka1 value for H3PO4. So, so that value, as it turns out, is right there on our chart. That's that 7.1 times 10 to the negative 3. So now we're ready to go ahead and do our calculations. So just remembering that Kw is equal to Ka times Kb. And so rearranging that to solve for Kb, that's going to be equal to Kw divided by Ka. And so 1.0 times 10 to the negative 14 is our value for Kw as a constant at 25 degrees Celsius. And interestingly, you'll notice that these Ka values were also collected at 25 degrees Celsius. So divided by, back to this, 7.1 times 10 to the negative 3. And when I substitute these values into my calculator, I get 1.4 times 10 to the negative 12. Okay. So now that what I figured out is that the Kb value for H2PO4 minus is 1.4 times 10 to the negative 12. Okay, and so really what that tells me, if I go ahead and I compare, I'm going to use just a different color here. If I compare the Ka2 value, which would basically be the Ka value, that would be the Ka for H2PO4 minus. So in this case, I see the Ka value is, times 10 to the negative 8. And the Kb value is 10 to the negative 12. So what that tells me is that H2PO4, which is amphoteric, because its Ka value is larger than its Kb value, that it's going to act predominantly as an acid as opposed to a base. It's going to have more acidic character. Of course, that depends on what it is reacting with. But by and large, that's true. Okay, let's take a look at a last question. Determine whether the amphiprotic bicarbonate ion is more likely to behave as an acid or a base. So based on the last few minutes of the last question, I'd like to see if you can figure this type of question out on your own. So pause the video and resume when you're ready. Okay, so to start this question, what I'm going to do is I'm going to write out the reaction equations for our bicarbonate ion acting as an acid and also acting as a base. And then we'll kind of go from there. So I like, whenever I have an amphiprotic substance, I like to react it with water. So regardless, I'm going to set both of these equations up with my bicarbonate reacting with water. And what it does depends on whether it's acting as a base or as an acid, right? And so if it's acting as an acid, we know acids are proton donors. And so as an acid, my bicarbonate's going to donate a proton. And as a base, it's going to accept a proton. So completing the rest of these reactions, I end up with the carbonate ion and a hydronium. That makes sense, right? My acid should be liberating hydronium ions. And then in the case where bicarbonate's acting as an acid, or as a base rather, it's going to accept a proton and become carbonic acid. And then produce the characteristic alkaline ion, my hydroxide. And so what I really need to look at if I want to answer this question is I need to compare, if it's acting as an acid, I want to know its Ka value. If it's acting as a base, I want to know its Kb value. And I want to compare the magnitude of each of those values. And so the Ka value for my bicarbonate, I'm going to look at the Ka2 value for carbonic acid, because bicarbonate is what forms when carbonic acid loses a proton. So the Ka2 value would represent the loss of bicarbonate's second proton. So that value I'm just going to write out here. It's 4.7 times 10 to the negative 11, right? So I'm going to also write that up here. Ka value is 4.7 times 10 to the negative 11. Let's calculate its Kb value. And remember that in order to get its Kb value, I have to get the Ka for its conjugate acid. And so the Ka value for its conjugate acid is that Ka1 for carbonic acid, which is this guy right here. So 4.4 times 10 to the negative 7. Okay? So let me just clarify this because we have a couple different Ka values here. So for HCO3 minus, the Ka value is that. And what I'm going to do now is I'm going to calculate the Kb value. So my Kb for HCO3 minus is going to be my Kw divided by the Ka for H2CO3, the conjugate acid. So 1.0 times 10 to the negative 14 divided by 4.4 times 10 to the negative 7. Again, that's the Ka for carbonic acid. Plugging that in my calculator. And so the value that I'm getting here is 2.3 times 10 to the negative 8. And so now I'm ready to compare my Ka values and my Kb values for my carbonic acid. So I'm just going to get my highlighter going here. So the Ka value for carbonic acid is this guy. And the Kb value, sorry, not carbonic acid, bicarbonate, pardon me, is this one, right? And so very clearly I can see that in this question, my Kb is larger than my Ka value for HCO3 minus, for bicarbonate. That is telling me that bicarbonate is acting predominantly as a base. Well, that is more likely to happen. Okay, so that was a little bit tricky, a few little steps to do there. I hope that when I went through it with you and broke it down, you're able to make sense of that. As always, make sure that you reach out to get some help if you need it, and I'm happy to assist.